work. I'm here to talk to everyone about Reflex, which is a little library that I built for working with changing data and interactive systems in Haskell. I'm going to tell you a little bit about why I built Reflex, and then I'm going to go into some examples, get into some code, and then if we have time at the end, I'll talk a little bit about how I actually built Reflex and sort of what the process of working on a sort of EDSL, something that touches very deep aspects of the programming language, what that's like. So before we get started, before I get off this title slide here, you'll notice that there's a chat room in my presentation. And you can go to chat.reflex-frp.org. And if you go there, and if my code works, then you'll be able to sign into a little chat room. It's an instant messaging platform that we built for this talk. Ali and Ali's my business partner at Obsidian Systems. We took a couple of days this weekend and a little bit of Friday to build this little chat app. And so that has a standalone client, which you guys can all access, and then it also has a couple of embedded clients inside of this presentation, which is also itself a Reflex application using Impress.js. So let's see if we can get someone else to comment in here. Anyone else joining this chat room successfully here? Once you get in, you'll have to click on the left on the Reflex channel. All right, and while you're doing that, I'll get started. So the first thing is, hey Adam. The first thing is basically, why would I do this, right? There are lots of existing front-end frameworks and back-end frameworks, and a lot of them are really great. There's been a ton of work poured into this. Google has done a ton of work on Angular. Facebook has done a ton of work on React.js. And all of these platforms and the ones similar to them have a lot to recommend them. They have a lot to offer, and they have a lot to learn from as well. But I decided to build my own, and it wasn't just because I wanted to do a whole lot of extra work. Really, the reasons are coming out of a couple of things. First of all, I wanted to be able to share code between front-end and back-end. Now, this is something that a few of the frameworks do offer today, and so I'm not necessarily, I could potentially have used one of those, but I did want to go into this particular reason, which rules out a whole lot of the existing frameworks. And basically, it's that when you're writing an application, dividing things into front-end and back-end or client and server is really often a very artificial distinction. It's a decision that you sort of are forced to make because you got to have some JavaScript running over here, you got to have some, C# or Go or whatever else running over here. And this is what people are trying to address with Node.js and with a whole bunch of other frameworks like that. It's just silly. It feels silly when you're writing the code to be like, okay, let me do this over here. All right, now let me do it over here. So I wanted to avoid that. And in particular, I wanted to be able to share three big things. APIs and protocols are the top one, because when you can share this between front-end and back-end, then you really start to lock down the interface between front-end and back-end. One of the biggest problems I've had in my previous work where I wasn't able to have the same language on front-end and back-end was that the front-end and the back-end would get out of sync. A developer would make a change on the back-end. Maybe they would even make whatever changes they thought needed to be made on the front-end, but they would miss things because there's no reason in the code that the front-end and the back-end have to correspond. It's all just in the programmer's head. And especially when you have different languages with different teams, that just becomes completely unmanageable. And that was probably the number one, but definitely in the top 5 reasons for QA bug reports at SketchMe and at some of the other places that I've worked. It's just constantly things getting out of sync. And you can do end-to-end testing, you can do all this stuff, but all of that stuff is more work, more just drag in the whole system. So if you can get it to be done automatically, that's way better. The second thing is the storage model and the query model. So it's not usually the case that you can share 100% of your database model between the front end and the back end, but there are a lot of things that you can share. So if you have a user record, maybe when I view my own user account page, most of that information is the same as what the back-end system is going to be processing. You're probably going to not have the password hash in there. There are a couple of other things that you're going to delete before you send it to the front end, but largely it's the same. And we should be able to make use of the fact that it's the same. We shouldn't have to do extra work to delete it and then extra work to recover the same structure again. And similarly with querying, right? If we know how to figure stuff out about what a user is, what it can do, all this stuff, we shouldn't have to rewrite those queries when we're doing it on the client just because we're on the client. And then finally, validation and other algorithms that run on the server side, you'd really like to be able to do those on the client side without having to hit the server every single time. So, with validation, if you have only server-side validation, then you often end up submitting a form, something happens, and then you get errors back. And at the very least, it's slower. Usually, it's also a worse user experience. It takes a lot of work to make it just be slower. But what we really want is for it to be fast, right? We want to do client-side validation. But again, we don't want to have to rewrite it all. If we already have a validation algorithm, we want to be able to use that on the client in addition to on the server. And that way we have a pretty good way of knowing that however we on the client expect it to work on the server is almost certainly how it's going to work because it's the same code. And this actually is a specific case of something more general called dead reckoning, which is very common in video games. And it basically means we don't actually know everything the server knows, but we're going to guess what's going to happen when we send this request to the server. We're going to do our best estimate of that, and we're going to show that to the user ahead of time before we actually get the response. And this is why you can actually play any real-time video game. When you shoot someone in Counter-Strike or deploy a unit in StarCraft, it's not happening at the exact moment that you do it. There's some latency, but you still see the result instantly. And the reason that that's able to work is because the game engine is running locally as well as on the server. So usually advanced dead reckoning like that is not done in web applications, but I think the main reason for that is not because it wouldn't be great. Of course it would be great. It's just way too much work. We don't have time, and there's too much code involved. So if we can reuse the server-side code that's going to actually make the final decision in order to make a preliminary decision, we can provide a better UX for free. Now, beyond just sharing code, having a common language for the front end and the back end actually has a huge impact on the team dynamics, in my experience. There's a really huge advantage to having anyone be able to work on any part of the application. Now, part of this is obviously just people can cover for each other, right? If someone's out of the office, you're more likely to be able to find someone who can fix that critical bug at the last minute. But it's not just that. It also means that there's less sort of worrying about who's responsible for what, right? If you're working on a feature, then yeah, you might want to talk to a database specialist, you might want to talk to other people on the team, but you don't have to submit, a feature request to the back-end team, wait for them to come back. It takes a lot of the bureaucracy out of working on a larger team when a single developer can just do a spike through the entire code base and usually have success with that. So that's a huge ideal. Now, in addition to the protocol level consistency guarantees that it provides, when you have a type-checked language like Haskell, you get an even additional benefit, which is that whenever anything changes on the back end, maybe really deep in the back end, maybe you change some database field or something like that, you're going to get type errors, right? And first they're going to appear in the back end, and then eventually you're going to propagate them, and maybe at some point they're going to propagate all the way to the API of the application. Now, if you're writing a split application where the front end is in JavaScript and the back end is in Haskell or in something else, then at that point where the changes hit the API, you have a couple of choices. One, you can never make breaking changes to your API. You can make sure everything is always backwards compatible, and that's going to take you about 6 times as long. Now, you can also go ahead and make the breaking change and also change the client. And this is why when you're on Pivotal Tracker or lots of other programs, they eventually say, hey, you got to refresh because we made some changes, right? That's probably because they've changed the API and they need the client to update as well. The problem is you're not actually going to know all the places in the front end that need to be updated. But if you have a type checker and your type checker spans all the way from the database to the DOM, then you can make all those changes and you can be relatively confident, even if you're changing somebody else's code that somebody else wrote, that you're probably going to get it all right. Or at least you're going to have a pretty good shot of getting it right and not getting too much feedback from QA. So that's a huge benefit. And another big thing, which doesn't really appear until you've been doing this for a little while, is that one of the big differences is that you no longer have to worry when you're making architectural decisions about where your software assets already are. Right? In a lot of software stacks, there are many different languages, and each language runs in a particular place. Right? So you might have some, PL/SQL, things sitting in your database. Probably that's a legacy thing these days, although some people still use them. You might have something that runs in your backend in C# or Scala or something like that. And then you might have stuff on the front end that's pure JavaScript. Now, if you decide that, hey, this would really run better in the database, or this would really run better on the client, you're not actually free to make that decision as an architect. Instead, you have to, you basically have to do a huge cost-benefit analysis. You have to say, well, it's going to cost us a ton to rewrite this C# into JavaScript, or rewrite this JavaScript into C#, and we're only going to even try to do that if the architectural benefit is huge. Whereas if your code is all in the same language, and more importantly, if it's all using a sort of similar set of libraries and a common set of vocabulary, then you can just say, hey, we should be running this on that server, or we should be running this on the client. It's just a matter of changing a module import, or something really trivial. So it really frees the architect's hands and frees their mind from worrying about these sorts of cost centers that really provide no value. And then getting away from just the code sharing aspect, because obviously you can share code in lots of different languages. There is a Scala to JS compiler. There's a Camel to JS. There are tons of stuff to JS compilers. And there's also Node.js, so you can run JS on your backend. Postgres even supports running JS inside your database if you want to do that. So you can do that, but then, for me, it wasn't just about sharing code. It was really that I had a lot of success writing Haskell on the back end, and I wanted to extend that to the front end as well. So I have a lot of reasons for choosing Haskell in particular as well, and I'll give you a few of those now. So the biggest feature of Haskell, in addition to the type system, which people love or they hate or whatever, I love it. The biggest feature for me of Haskell that distinguishes it from everything else is that Haskell is one of the very few languages where you really do write pure functional code almost all of the time. It is very serious about pure functional stuff. There's a lot less cheating in some languages. There's sort of an ideal of pure functional, but people are very readily willing to compromise it. Usually this is strict functional programming languages, because in a strict language, it's much easier to reason about when your imperative code is going to run. So you can sort of say, well, I'm going to expose a pure interface, but I'm going to do all my implementation in imperative style for performance reasons or whatever. But in Haskell, because it's lazily evaluated, it's almost impossible. It's very, very difficult to get that stuff right. So generally, people don't try. And a bunch of academics have looked at it and said, well, okay, I understand that you guys aren't cheating. You still need good performance. And the net result of that is that they've contributed probably the best optimizations in any compiler to GHC, which is the main Haskell compiler. The optimizations in Haskell are just phenomenal, and the net result is that idiomatic Haskell that's written at a very high level often performs competitively with C. And that's, I don't even know. I mean, it's hard to even comprehend how much simplification and rewriting is done to a Haskell program to achieve that kind of performance. Now, the reason that I love pure functional programming is because it enables two basic things, which are key to the ability to reason about, maintain, and improve software. Equational reasoning means essentially that we can refactor on both small and large scales extremely easily. See, so in Haskell, when you see an expression like x plus x, and imagine that x could be a much more complex expression as well, right? So if you see an expression being added to itself, you can change it to just multiply by 2. That might impact your performance a little bit, but it's not going to impact how the program behaves. And we have a really strong guarantee of this. Now, in a lot of other languages, if x were an expression, for example, that included a function call, that function call might print something to the console. So on the left, you'd get 2 print statements, and on the right, you'd only get 1. Or it might go out to a database and do a transaction. So on the left, you get 2 transactions, and on the right, you get only 1. It might launch the nukes. You don't know what it's going to do. So you definitely want to launch the right number of nukes, and the advantage that Haskell has is that you know nothing is going to launch the nukes unless the type system specifically says this is a nuke launching thing. So it means that we can refactor without fear, which means we can refactor a lot more frequently, and that means our code bases stay a lot cleaner. Now, local reasoning is a related concept, but this is really all about context. In a lot of languages, if you want to understand what a function is going to do, or what any code is going to do, you're going to have to look at a lot of the program to figure that out. You know, if you've ever had to trace through, you know, some, well, I don't want to call it any particular language, but some rat's nest of callbacks and like other interacting code to figure out what's going to happen, then, you know, you're familiar with this. In Haskell, because we know that a function doesn't do anything aside from take its argument and produce its result, we don't have to worry about that. If a function isn't taking something, it's not using it, right? Everything in the global context in Haskell is constant. It's something that, you know, you might have to look up, you know, the definition of a function or something like that, but it's not going to change at runtime. You don't have to worry about any interactions between different modules. Basically, every interaction that might cause you some concern has to be explicit. And this is huge. This is just incredibly important. It means that it's much quicker to understand what someone else's code does. And it means that even if you don't fully understand some code, you can still work with it. And those are huge benefits in my mind. So another reason that you need code to be as independent of its context as possible is because you want it to be reusable. And sort of by definition, if something depends a lot on its context, then there aren't that many contexts in which it's going to work, right? So obviously functions that are super simple, like addition, can be used in many, many different contexts because they don't depend a lot on the environment. But something that says connect to my, you know, AWS-based Postgres database, well, that's only going to work in a very small subset of configurations. And if you screw up the configuration, it's not going to work. So we always want to limit the dependence on context as much as possible, and we want to be very explicit about whatever dependence we have on context, so that, you know, someone can look and say, oh, that requires AWS and Postgres, so let me hook that stuff up. Now, the net result of this is that Haskell has been really amazing for a very long time with batch systems. And a batch system is really any system that takes most or all of its input at the beginning of its execution and produces most or all of its output at the end of its execution. So compilers are a classic example of this, right? You take a source file, you do a whole ton of stuff, and then you return a binary. Web APIs are pretty similar. You do have some server stuff going on all the time, but largely what you're doing is, okay, here's a request. Let me process the request. Okay, let me return the response. So each request in a web API is basically a batch system, if you ignore video streaming and things like that, which are also important, but, you know, most web APIs are sort of batch driven. And I think that this is why, you know, for me, Haskell has been working very effectively in terms of building web servers, building anything else that has this structure. The problem is that until recently, it wasn't really possible to program a GUI in that sort of functional style, because GUIs are exactly the opposite of batch systems. They take some input, then they produce some output, then they take some more input. They don't even know which input they're going to get when. So it's this complex dance back and forth between the user providing input and the program providing output. And Haskell has a way of doing this that looks a lot like an imperative language. There's a type called I/O, and that's how you represent an I/O computation. It can read things in, it can write things out, it can modify stuff on the screen, it can do whatever you want to do. But essentially, it's an imperative language embedded into Haskell. And although it's one of my favorite imperative languages, I would use it for anything, even if it was heavily sort of fundamentally imperative, which I don't know if that actually exists, but even if something really felt right to be imperative, like maybe writing a console app, then I like I/O, I like the way it works, but it's still imperative programming, and I would like to get to pure functional programming in as many contexts as I can. Now, in Haskell, even if you're writing in GTK or one of the other common UI frameworks, you're basically writing I/O. And this means that you're writing callbacks, you're writing mutable state variables, you're doing all the things that are typically associated with writing GUI code. You're just doing it with a slightly nicer type system and maybe a couple of other advantages, but the fundamental problem is that it still doesn't scale, still doesn't work. It's just as bad in many ways as writing JavaScript or writing anything like that. So the response to this, really the only compelling response that I've seen, is functional reactive programming. And this is something that was initially conceived in about the mid-90s by Connell Elliott and a few other people, Paul Hudak at Yale. And the idea here is that we're going to write a way of doing all the same interactive computations that we can do in any imperative system, but we're going to do it in a way that is entirely pure. Now, I'll take a minute to define what pure means here. Really, pure means that a value, once it's created, can be used or not used. It can be consumed once or many times, and it doesn't matter how many times it gets consumed. So if I take a pure value and I hand it to this part of the system, I hand it to this part of the system, the fact that I've given it to this system is not going to impact how this system is going to deal with it. And that's really important because it means that I don't have to worry about where that value has gone. Now, this is in contrast to an object-oriented system or some system that's based on a lot of state variables, where if I hand a pointer or a reference to this module, it might do stuff to that pointer or reference, right? And that might impact the way that this one is able to do it. So, like, let's say I'm using a Unix, socket, right? So a socket lets you send and receive data. Well, if I take my HTTP protocol socket and I hand it to just this system, it speaks HTTP, it gets an HTTP response, it's beautiful, works just fine. If I hand it to just this system, it speaks HTTP, great. But if I hand it to both, all the requests are going to get interleaved, the responses are going to get randomly divvied up between them, and it's going to be completely broken. So that's an example. A socket is a perfect example of an impure value. FRP gives us tools where we can write our entire interactive program without ever using any impure values. All of our values are going to be pure. All of them are going to be the kind of thing that you can pass around or delete or let garbage collect or anything like that without worrying about it. And that's the key there. And this is what gives us equational and local reasoning. Because we can do this passing around, things work like they do in math, not like they do in QBasic. All right, so the key idea here is basically that we're consuming input and producing output over time. And so FRP gives us a semantics for dealing with that. And the primary components of this semantics are things called events and things called behaviors. An event is a stream of values that are given periodically, and they're pushed through the system. So an event can be used to model something like a mouse click, right? So if I look at the mouse and get an event representing the clicks off of it, each event might be a pair of coordinates, and then that event is going to fire whenever the user clicks the mouse. Now, where it comes from, I don't know, and I don't care. That's the responsibility of the GUI framework to provide that to me. And then if I need to provide that data to someone else, what I can do is I can transform that event and provide them the result. I'll get a little bit more into that later. But the other sort of semantic contribution of FRP is called a behavior. A behavior is a slightly different thing. A behavior is something, it's more like a variable. It always has a value, and you can ask it what its value is at any given point in time. And you can't set its value, but you can get it. So again, nothing you can do to the behavior is going to change what it does. But that's why it's a pure value. But it can still represent this whole timeline of values that are changing. So Reflex provides events and behaviors, along with a few other things, but that's the primary thing it provides. And it basically adds those to Haskell. These are new data types. It's not actually written as a compiler extension or anything like that. It's just a library, but it's a library that uses rather hairy, low-level stuff to essentially add these new semantics to the language. And I do think of them as language-level features because they tend to pervade your code, right? So to me, something that's language-level is something where you kind of expect everything in your application to depend on and to depend on the semantics of these aspects of your language. And then you can add things on top of it. So Reflex supports writing transformers, which you could use to take your standard version of an event or behavior and transform it so that it also provides error isolation or call stacks or something like that. And these are things that just sort of go all the way through your code. And then Reflex is built to work with both the native Haskell compiler, GHC, and that'll produce binaries for Windows, Mac, and Linux. And it's also designed to work with GHC.js, which is a phenomenal piece of work mostly done by one guy, Loud to Stegeman, who basically wrote a JavaScript backend for GHC. So it gets the benefit of all of the optimizations of GHC. The type checker is the same. All of the front end of the compiler is the same. He's just replaced the LLVM-based binary generation stuff with his own very efficient JavaScript code generator. And the net result is that you get JavaScript that runs, within maybe, certainly within an order of magnitude, in my experience, more like a multiple of 3 of the actual regular native Haskell code. And that's pretty darn good for an interpreted language. Now, the main thing that I've built and worked with using Reflex is Reflex-DOM. And Reflex-DOM gives you an interface to the document object model, the in-browser programming toolkit, that is all Reflex-based. So there are no callbacks. Everything in Reflex-DOM is done using events and behaviors. You never have to write a callback. There is an escape hatch for you to write a callback if you, for some reason, are doing something I haven't foreseen. But realistically speaking, you can write very complex applications without ever touching a callback, without ever writing any IO-based code. Here's something that gives me input. I'm going to take that input, pipe it into this output, and it's done. And so this is something that Ali, my business partner at Obsidian, and I have been working on for a while. And this is something that we use in most of our work. Now, it's probably pretty obvious at this point, Reflex-DOM applications are written in Haskell. And They run in the browser, and they use FRP for everything. And that's not just the I/O, like I just mentioned. It's also the internal application state. When you're doing your sort of model view controller style architecture, or really, it supports a wide variety of architectures, so you can really use whichever one you want. That's all done with the same event and behavior-based primitives that all your input and output is done with as well. So that actually makes it really easy to encapsulate stuff, wrap it up. It doesn't really care whether it's talking to the outside world or it's talking to some other part of the program. It doesn't know, it doesn't care, it just works. And it's also designed to work with standard web backends, so we can talk, JSON or WebSockets or whatever you want. You can also use at least 80 or 90% of the Haskell libraries on Hackage. They pretty much, a shocking number of them work perfectly in the browser. Pretty much anything that doesn't have a C library dependency is going to work, and some things that do. And so you can hook it up to anything that you may already have kicking around. So now I'm going to get into a couple of excerpts out of the code for the application that I mentioned earlier, the one that's running in this and at chat.reflexfrp.org. This is the API for reflexfrp.org. This is the whole thing. And basically what we have here are two types. This top type, called up, represents messages that can be sent from the client to the server. And you can see there are 5 of them. And you can add a nick, that's basically saying this is who I am. You can remove a nick, basically saying I'm no longer this person. I did it that way just so that we could support multi-nick login if we wanted to. There's no authentication or anything like that on this. It's just a little example app. I was optimizing for simplicity, not usability here. But even adding authentication wouldn't be that much harder. This is all sent over a WebSocket, so if we added some kind of authentication protocol to the add nick interface, then we'd basically be able to handle everything that way. Now, we also can join and leave channels, and we can send messages. Now, each of these types is specified in a little bit more detail in another part of the API source code. But I think they're pretty self-explanatory. Now, down here is there's actually only one kind of message that you can receive right now. That's this down message. And that just gives you a message that's been enhanced with some stuff like timestamps and other server-generated data. So it's very easy to just wrap that type in an envelope. This here is actually an implementation detail. You wouldn't usually see this in a real application, but basically this is just so that the JSON format doesn't change any more than necessary when we start introducing more and more commands, because the JSON format depends on whether you have just one kind of command, then it'll be a little bit more concise, or if you have multiple commands. Now, one really cool thing that we can do here is this command. Each of these is generating all of the code necessary to encode and decode these types as JSON on both backend and front end. And this is done using something called template Haskell. It's a little Haskell program that runs at compile time for both the front end and the back end. And it's going to generate all of the Haskell code that does that encoding and decoding. And so, we just use the default options. You can customize this a little bit. It's provided by this library called ASIN. It's just pretty much a standard Haskell JSON library. Facebook uses it for some of their malware detection software at pretty enormous scale. And yeah, so this is all we have to do for all of our serialization code, front end and back end, and we know that it's going to work exactly the same on front end and back end because it's the same code. So here's a little bit more of that API. You can see that these are also pretty straightforward. They get their own derived JSON later in the file as well. And these are going to be just sent as little JSON objects. Your from is Nick, and Nick is just a way of saying this is a string, but we don't want to mix it up with other kinds of strings, so we do that. Destination is going to be either a person or a channel, and then the body text. Very straightforward stuff. Envelope here is a parameterized type. So this would be like a generic in Java or a template in C++. And this will just take another type and it'll wrap it with a UTC time as well. And so we get all kinds of stuff for free. We get show and read for debugging. That'll let us print things out to the console easily. All this stuff is happening for free. All we have to do is specify the data structure. All, serialization, reading and writing, all this stuff is handled for free. Now, here's an example of something that's actually doing Reflex-DOM code. This is backend code. So this is not Reflex-DOM. This is Haskell-based snap on the backend. And so here we can say this function basically just says, look, I'm in an HTTP session, and I would like to transform that into a WebSocket session. And on the right-hand side, after this $, we just write our WebSocket server logic. So that's really simple. And for this particular server, we don't have any persistence or anything like that. So there's just one big mutable state variable in memory that holds all of the server state. And if you go to that link, then you can actually they'll have to go to the chat branch of that. But if you go to that GitHub repository and look at the chat branch, you can actually see all this code in the chat directory. And so if you want to follow along, go ahead. But basically here all we're doing is we're saying, all right, we've received a message. That's going to be this value up. And now we're going to case on it. So this lets us select which bit of server logic we're going to do based on what kind of message we received. And this has already been decoded from JSON. We don't have to worry about that part. So in the case of an up message, or rather in the case of a message being sent up, then we just get the time. We look at the current server state to figure out who's listening for that message. Then we do some pure functional logic here. This is in a let statement, so it can't do any I/O. So this is just saying, look, get the connections for that particular destination of that message. And then also, if we're sending it to, isLeft is just saying if we're sending it to a person, then also get all the connections for the sender so that we can show them the message they sent. And then we just loop through these and send all of the corresponding down messages here. So pretty simple, straightforward code. As you can see, this is actually the most complex code in this server. All the rest of this stuff is just, when we add a nick, then, take our state and add it there. When we remove a nick, do that. And all of this is happening atomically. All we have to do is say, look, we want to make a complex change to this variable. We want it all to happen at once. Bam, it happens. We don't have to worry about synchronization or mutexes or locking or anything like that. In a more, larger system, you're going to have multiple servers, so this does get a little bit more complex. But having this basic capability is pretty great. Well, right now, I think that having a program with just one variable, which is not a global variable, by the way, it gets passed in right up here, is pretty functional as far as web servers go. But yes, in the future, we can do it more functionally. And in fact, in the future, I think that FRP is going to get used on the back end as well as the front end. But we don't have a Reflex-based FRP back-end system yet. So until then, I'll just try to minimize the imperative code instead of eliminating it. All right, so here's where we actually send our requests to the server. This is a little bit more complex here. And actually, the front-end code in general is most of the complexity of this app. But basically what we're doing here is we're saying that when we receive this send event, what we're going to do is attach our current nickname to that to create a message. And then we're going to turn that into one of these up message things. And then we're going to put it inside of a list. And then we just, then basically that gets combined with all these other events. So what's going on here is that mconcat is going to take a whole bunch of potential messages that various parts of the front end could be wanting to send to the server, and it combines them all. And the interesting thing about this is that because of the structure of FRP, we know that this list is the only place in the application that anything is sending messages to the server. Because this is what goes into the actual WebSocket function. And because we know that FRP values can't be modified once they're created, and because we can see here that this one is created by mconcating these other ones, we know we're done. Like if we ever wonder, like, oh, what's sending this message to the server? Well, it's something in this list. And if we want, we can put trace statements on each of the things in this list or on the list as a whole or whatever. And we don't have to worry about tracking down, okay, what messed with WS up after app initialization. It's all very straightforward. Now, I'll go through a couple of these other cases. You know, when we want to remove a nick, all we're doing is we're basically saying whenever the current nick changes in that text box in the upper left, then we're going to take the old current nick, we're going to put that into a remove nick, and then just like with the up message, we put it in a list and we send it out. Now the reason these are all going in lists is actually because you might do a UI action that causes multiple messages to need to be sent to the server. And so what mconcat does is it actually concatenates those lists together. So if, for example, well, yeah, actually, this is the example. Oh, sure, but even this one here, this is an example too, because when you change your nickname, you can see updated nick here and updated nick here. Well, it's the same value, so it's always going to fire simultaneously with itself. And so when both of these go through, you're going to get some pretty nice guarantees here. So you're going to know that because it's the same value, it's always simultaneous with itself. And actually that's true even if you transform it somehow. No matter what you do, the simultaneity is going to be preserved. And this sort of goes all the way back to that text box. So when there's one origin for an event, it's going to be simultaneous with itself and it's going to be handled properly all the way through the system. There's no non-determinism. If you've worked with a lot of other like PubSub or other ways of handling this kind of stuff, you often end up in a situation where a bunch of callbacks fire in this enormous tree, and one thing receives the message, passes it along, and then at the end, all of those messages arrive in a different order, and you have no idea what order it's going to be. Even if it's a fixed order, you can't read the source and figure out what that order is going to be. In this situation, because the simultaneity is preserved by the FRP system, you know that the order is always going to be the order in which they appear in this list. When you concatenate the lists, they're always going to stay in the same order that they were in before. So we know that we're going to send the remove nick command before the add nick command always. And we also know, by reading this list, that these are the only places in the entire application that remove nick and add nick are sent. So we actually can, just by reading this code, we know that we're never going to forget to unsubscribe from the old nick. And then, yeah, if we go down lower here, we can also make sure that we leave all the channels that the old nick was in. And that's a situation where we can combine a whole bunch of behaviors. So updated nick is an event, right? That's something that happens sometimes. The nick gets updated. Current nick and current chats, anytime you see current, that's a behavior. You can ask what the current value of something is. And we can use these operators here, which are, they look kind of funny if you don't write much Haskell, but in Haskell they're pretty standard. And basically these things say that we're going to take something that's inside a container, so in this case inside of a time-varying value, inside of a behavior, and we're going to combine it, retaining the container around it. So if you had, so basically this is like taking a couple of timelines, putting them next to each other, and zipping those timelines together so that at every point in time, the result is going to be that combination of their current values. All right, so any questions about the last couple of slides or this one?
Yeah, do you mind going back and explaining again why you'll never forget to remove an old thing?
Well, so it goes like this. Basically, we know that the only places that a nick is added or removed are in this list, because we know that this list is the only source of data being sent to the server. Now, we can also read through this list and see that remove nick and add nick right here are the only appearances of those constructors in this. And we can also actually see that every other alternative provides a different constructor, right? So we can right now rule out the possibility that remove nick or add nick are caused by anything else in the application. The second part is that we can look here and see that updated nick and updated nick are exactly the same value here. So whenever that event occurs, it's going to occur in both places, and it's always going to be simultaneous because it's the same value. A value is always simultaneous with itself. Then we can see that this one, what tag here does is it takes the current value in its first argument and the event in the second argument, and it replaces every occurrence of that event with the value at the time of that occurrence in the first argument. So it's basically like if you imagine this event coming by, every time it comes by, it grabs the most recent value of this behavior. And the way this nick value is set up is that current and updated are always in lockstep with each other. So when updated is not occurring, then current is just constant. And when updated does occur, then current is at that exact moment going to have the old value in it, but at every future moment, it's going to have the new value in it. And that's a law of this data structure provided by Reflex called a dynamic, which is basically a combination of an event for updates and a behavior for old values. Tag just combines a behavior and event, so you end up with an event with the same times of occurrence, but different values. So we know, based on that logic, that the output of this tag is always going to occur simultaneously with this value, which means that these two are always going to occur simultaneously. And we also know that whenever these do occur, this one's going to have the old value, and this one's going to have the new value. And so anytime the nick changes, we're going to simultaneously issue a remove nick and an add nick command. And furthermore, we know that there are no other times that either of those commands will be issued. Does that make sense?
And they're in that order.
And they're in that order. That's right. Because whenever things occur simultaneously in an mconcat, then they appear in the same order that they appear in the argument to the mconcat. So we've got a list of things here. Each one has an event of a list inside. Mconcat is going to take that list of event of list and turn it into a event of list. So it basically strips off the outer list and just gives you a single event with all of the inner lists that occur simultaneously smashed into one. All right, so that's the end of the code examples. The code is on GitHub, and we will be updating it from time to time to make it simpler, to maybe add a little functionality. Please feel free to send pull requests. We're not going to try to turn this into the next Slack, but anything that contributes something pedagogically useful will definitely be happily accepted. So over the past, so we released Reflex in the end of March, and since then there's been a lot going on in the community and at Obsidian Systems regarding this. And so Obsidian Systems was coincidentally founded around the same time that Reflex came out, and we do most of our work with Reflex, and we do almost all of our work with functional programming. And that includes things like the Nix package manager, which is a pure functional Linux package manager. It's pretty cool too. And pretty much, we use a whole ton of Haskell stuff. We occasionally use JavaScript for glue code and other things that require it. But we're a pretty dedicated functional shop, and it's working pretty well so far. In the last 4 months, we have grown from just me and Ali to 7 people doing consulting work, and and I think our clients, excuse me, I think our clients have been pretty happy with the results we've been able to offer them. I think it's not uncommon for a tech stack with Haskell and Reflex and that kind of stuff to be able to move, almost an order of magnitude faster than the other kinds of tech stacks that I've worked on personally. In the last 4 months, we've also done a lot of work with a huge number of community contributions on documentation. That's pretty much been the main focus, because when we first launched, it was really, we had done some testing with Ali and I and some of our preliminary clients to make sure that everything was solid. We knew that it basically worked, but it wasn't as documented as we wanted it to be. So we've been working towards that. So now there's a quick reference sheet. There's some really great tutorials. There are a lot more examples, like in this Reflex examples repository, and there's been just a lot of discussion of what are the pain points and how do we make stuff easier for beginners. We've done some great additional testing. So we now have a 37-line long, totally simple, pure functional, not usable in production because it's way too slow, but a very simple and easy to comprehend drop-in replacement for Reflex. And what we do with this is we cross-test it all. So it functions as basically a mathematical specification of what Reflex is and what it does. And we have hundreds of lines of tests that basically say, well, we've got our theoretical semantics here. That's implemented as a Haskell program. And we've got the high-performance implementation of Reflex, and we want to make sure that they work exactly the same. And so, at this point, after people hammering on it for 8 months and having hundreds and hundreds of tests for that, we're pretty confident that it does behave exactly as the semantics expect it does. We've also been adding benchmarks. There's some great work that's been done in the last month or two to get a very comprehensive benchmarking test suite, and we're working to get constant, continuous regression testing in place for that. That'll enable us to move a lot faster in terms of adding features to Reflex, making sure, because basically performance is extremely important to us, so we would rather not have a feature than introduce a feature that's going to kill performance. And so, with really great benchmarking suites in place, we're going to be able to really, I think, drive a lot faster. And then we have had a couple of bug fixes. There was one really interesting one involving the garbage collector and an interaction between a particular optimization that was done sometimes and a particular part of the garbage collection algorithm, which only occurred on native and didn't occur in GHCJS. And that was very helpfully fixed by a fellow named Benno Fumstuck, which I'm sure I'm mispronouncing. And I would say overall there have been a couple of bugs fixed, but actually a lot fewer than I expected. The community has contributed a huge amount to this, and I definitely want to thank all the people out there who helped. Reading through the Git logs, some of the names come out a lot. Salzar, Benoffs, that's the guy who fixed the GC issue. DBB NRL, Jeffrey Rosenbluth, K01, and Paldepind. And then there have been a ton of people who have given feedback on the IRC chat on Reflex FRP. That feedback is probably, in aggregate, the biggest contribution of anything, because that's what helps me and the rest of us at Obsidian Systems figure out how we can better support these libraries, how we can do things that are going to really make people more productive. And then Reflex-DOM has also seen a lot of improvement. We went from having just sort of some one-off WebSocket support that we had done in-house to now having a nice open source official WebSocket connection library. We also have SVG support built in, and actually it's not just SVG, it's anything that is built into browsers using XML namespaces, so we can support MathML and all kinds of other crazy stuff. We've started building out some more complex widgets, composable bits of GUI logic. So we have something that Ali added a few months ago that was basically an infinite scrolling list, but not the annoying kind of infinite scrolling. You know how it's always annoying when you're on Twitter or whatever, you scroll to the end, and then it slowly loads the next page, and then you scroll again, and then it slowly loads it again. Well, what this is instead is basically, it gives you the whole scroll bar up front, and then whenever you scroll to a region you haven't seen, it figures out exactly what data is needed and passes that off to the rest of the UI. And so we've hooked that up to database backends, we've hooked it up to other stuff. It's a very general purpose way of just saying, look, I have way too much data to throw into the DOM right now, but I really want to give the user the feeling that, hey, there are a million items in this list, and you can go to whichever one you want right away. And again, there have been a couple of people who have really provided a huge contribution here. Paldepind, DBB NRL again, Barteveld, Danza, Mighty Byte, Nomita, and Menu. And those are just the guys who I found tonight when browsing through the Git logs. But without their contributions, we definitely wouldn't be nearly as far as we are. And of course, thanks to my business partner and also everyone else who's working at Obsidian Systems. They've really put in a huge amount of work to make this stuff do what we need it to do what the community needs it to do, and do it all really in a slick and high quality way.